Machine learning is a massive field full of creative and complex ideas. Probably the best place to get started is with scikit-learn. Join me today as we use this tool to take a small step into a much larger world. I'm Gregory Topwine with GNT Learning. On this episode, we're going to build some basic code using sklearn. Our goal here is not to focus on a specific model or data set. Instead, we want to get the boilerplate down so that we can use sklearn and all the tools and packages it has available to us as we go forward. We're going to spend a lot of time focusing on debugging the most common errors that frustrate and perplex new users. And in the end of this, we're going to have some nice core jumping off place so that you can get into the field of machine learning. All right, let's jump right into the code. Now, before we can develop any sort of model and explore machine learning, we first need to have some data to work with. To that end, we're going to use the package pandas to help us get our data. Now, pandas is a pretty rich package with a lot of features, and we don't really want to dive into that tool today. Instead, we're just going to be using it for its most basic functionality, which is going to be reading a CSV file in from disk so we can begin looking at that data. Okay, we're going to be doing that using pd.readcsv. And as you might expect, this reads a CSV file. Now, the file we're looking at today is something that we prepared ahead of time. Now, this data is available through sklearn directly. Just prepackage it here as a CSV because the most common way you're going to get data, especially when you're first learning to work with things, is in the form of a CSV file either downloaded or has been handed to you from somewhere. Now, so we can go ahead and get that data in and take a look to see what we have. And what we get is this nice little data table that has 6 columns of data and a number of different rows. Now, this data in particular is for some sort of physical fitness data set, has some information about exercise and these health metrics. But today we're not going to focus so much on the details of the data. We're really just going to be using this sort of as a black box of numbers that we're going to evaluate just to see how we can use the tools. The reason we're using this particular data set is that it is very clean. You notice that there's no missing values here. Everything is in a nice format. It's numeric. And there's really nothing special we have to do to handle the data. In machine learning, that actually can be the vast majority of your time is cleaning up messy data and dealing with that problem. But today we're just going to work on focusing to get that core idea of how to do a fit. So we have a pretty clean data set to work with. Now, I'm going to note here that I used df at the line of the Jupyter Notebook to display it in this kind of nice format. Something that a lot of people aren't aware of and is pretty handy is that most implementations of Jupyter Notebook will allow you to use the display command to do this as well. Now here it's not going to look like anything different has happened. However, this display command, like the print command, allows you to do this in the middle of a block of code as opposed to just printing the last line automatically the way Jupyter Notebook does. Now, it won't quite work for everybody, but if it does work for you, I recommend getting the habit of using display rather than just putting df to show your data frame at the end of a line. Now that we have some data loaded, let's go ahead and pull some actual numbers out to use for our model. Right, so the two things we're going to use here are going to be the column for the number of chin-ups that were performed, called chins, and the number of sit-ups performed, called sit-ups. All right. Now, this is the easiest way to pull data out of a Jupyter Notebook is to use data frame, open square bracket, and the name of a column. Again, data frames are a very rich tool, and so there's a lot of other ways of grabbing the data and more complex things. We're just keeping it to the simplest, most direct form for now. All right. So we can go ahead and run this, and if we want to make sure that we're getting something that looks correct, we should take a moment to evaluate what we're getting. And we see here that the x values are the values corresponding to the chins column from above, and we also are actually getting a series object, so we have the index that goes with them here. We don't really care about this index for the most part here. We mainly care about the values, but we are getting a series object as a result of pulling a column out of a data frame. Now, the first big idea that we have here in machine learning is that we want to take this data to make a model, and we want to know if our model is any good at the end of the day. So we don't want to actually just fit all the data and hope we did well. We want to split the data into two sets called a training set and a testing set. That way we can train on the training data and then use the testing set to see if our model is actually a robust model that's doing decently. So this is going to be the first thing we pull from the sklearn toolbox. Right. So I'm going to go back up to the top here, and I'm going to, from sklearn, I'm going to import the train test split. For those that have not done a lot of Python work before, you'll find there's a couple different ways you can import pieces. When we imported pandas, the way we did it was we just use the import command directly and use this as keyword to rename it to something a little more convenient. Another way to do that is using the from keyword along with import to say, I want not to bring in the entire sklearn package. Instead, I want to bring in some small piece of a much larger whole. And in this case, there may be multiple parts to the path. All right. Now, the other thing I want to mention here is we're going back up to the top to do this. It's easy enough to get into the workflow of going through your notebook and saying, oh, I need this new tool, let me just import where I'm at. It's just good practice in general to bring your imports back up to the top of the script so that there's a little bit of organization overall. When you work in a Jupyter notebook, you should be revisionist. Your goal is not to have a list of the things you tried in order. Instead, is to have an organized way of approaching the problem. So go ahead and put your imports back at the top. And of course, when you put them back up here, make sure to run the cell, or else you'll be very confused in a little bit. All right, so now you've imported test train split, or rather train test split. And we can use it down here, train and x test. All right, equals train test split. So this train test split is going to do is it's going to split both the x data and the y data into two different groups, a training set and a testing set, as mentioned. And because we have x and y, we have to split them consistently with each other. So we pull out the x's that correspond to the y's that get pulled for the test set. When we do this, we have to specify what fraction of the data set we're going to use for testing. Now, there's a lot of different heuristics for how this goes about. We're just going to do point 2 for the day and discuss the actual splitting itself in a later video. And the other option we want to provide here is random state. Now, what random state says is, well, sure, you can split this randomly and get some different values, but if I come back and run this code again, I'll get a different random split. I want a random split, but I want to get the same random split if I go back and rerun this code later, so I get the same results. In simple terms, it just means you need to pick a value here, doesn't really matter what it is, and just make sure you use that same value when you rerun the problem. We can go ahead and run our test train split, and then just to validate that things look okay, we can look at xtrain, and we can see that we have a shuffled set of values that no longer corresponds to the table above, if you want to double check. And you also see, because we have this index column, that the index is shuffled. So you can see we have 0, we have 1, we have 2, we have 3. And if you look carefully, you'll notice that there's some number missing. In this case, 7 is not part of the training set. That's because it is now in the test set. All right. And behold, it is indeed in the test set. And likewise, you can look at the y, and we'll see that rows 9, 11, 7, and 14 are in the y test set as well. So we verified that our data looks reasonable. And so now that we've done that, we can start turning to the problem of actual linear regression. All right, so here we need to go up again and do another import. This time, we're going to import from sklearn the actual model we wish to use. So in this case, this is going to come from linear model. And we're just going to do linear regression. Now, we're doing linear regression because it is basically the simplest model possible. You can make some arguments about other models theoretically being simpler, but this is about as simple as it's going to get. You'll notice the import style here is very similar to what we did for model selection, and we're just pulling it from a different part of this very large toolkit. In the first part, we were pulling something to do some pre-processing work, and now we're pulling from one of the many models that are built into sklearn. Again, remember to run your cell. We can now go ahead and instantiate an instance of our linear regression model. All right. So what this means is that we use this linear regression we imported to define a model object. And this model object is going to be what takes in the data and handles it and moves things around. Now, for linear regression, our problem is simple enough that we can just use the default setup by using pair of parentheses here and say instantiate the model. For many other models in sklearn and other places, you will need to provide additional optional arguments. For a decision tree, it's the max depth. For k-nearest neighbors, it's the number of neighbors to look at, etc. But again, linear regression is simple, so we have no parameters we need to put in here. Next, we can go ahead and fit our model using model.fit, and we can train it on the training set, and then we can go ahead and make a prediction based on the test set. X train. Now, if we take a moment here to glance at this piece of code, you'll notice this is very generic in the way it's written. And this is actually how most of the models work in sklearn. So you define the model, you use .fit, hand it the data you wish it to fit, and then use .predict to get predictions on some other data set, or potentially on the same data set if you just want to see how the training itself is performing. The only real exceptions you see to this are if you're doing a model that is unsupervised learning, you don't have a Y value here. And unsupervised learning is something like clustering, where there isn't a target variable. Instead, you're just seeing what groups they naturally fall into. And so no target, hence no Y value, hence the fit does not require a Y. But in general, this is the way you do an sklearn fit, and this is something you can use across all the different models built into it. Which is one of the really nice features about sklearn is that you don't have a different syntax for every different model. They all follow this really exact same boilerplate. Now we're going to run this, and we're going to get an error. Now, everything I've done up to this point looks very reasonable, looks very normal, but somehow we broke it. So when you first are starting off, you're going to see errors like this, these massive wall of text, and go, whoa, what did I do wrong? Take a moment, and for those new to Python, the answer, generally speaking, is you scroll to the bottom, and you look down here where it says that the error actually is. A lot of times you'll get very nice specific error messages if you know where to look. So here it says value error expected 2D array, got 1D array instead. And it spits out the exact values in the array, and then gives us a hint that, well, we need to maybe reshape our data either using array.reshape with -1, 1, or possibly doing it with array.reshape 1, -1, depending on whether we have a single feature or a single sample. All right. So say we're new to Python, we're new to machine learning, new to sklearn toolkit. There's still a bit of confusion here, but we have a couple things to hang our hat on. First of all, we have the exact set of data that it is causing the problem. And we know there's some problem with 2D versus 1D. Well, if you have a good memory, you'll realize we've actually seen this exact set of numbers before. This was our X train. So here we go. So you can see, 15, 17, 13, 4, 15, 17, 13, 4. Okay, so we know the problems with X train. The other piece that would have been helpful here is this bigger wall of text is the full traceback of what went wrong. A lot of times it's got more detail than you want, but often enough, somewhere near the top, you'll see the actual code that you wrote that caused the issue. In this case, it was the model.fit X train, Y train. So the regression itself ran all right, but something broke on this line. And under the hood, that caused something to break here, 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 and further down. But we don't control that, and we can generally assume that the package is working correctly. Instead, we control what's going on at model.fit, and we see that something is wrong with our X train. Well, the error here is one that you're going to run into often when you first get started, and it is to deal with the shape of the input, 2D versus 1D. What we did, way back at the beginning here, is we said x equals df of chins. We said x was one column of data from our original data frame. Well, it turns out that sklearn makes the assumption that, well, you're going to give it a two-dimensional input because you could have done this in a way where you give it 2 columns or 3 columns of data to work with. And so in general, sklearn is prepared to take multiple inputs to do multivariate linear regression. And as such, when you only give it one, it causes it to be a little confused about what you mean. And the confusion is because since it got a 1D object, it's not obvious to it if it's supposed to be that this is just one row with a lot of different values, or one column where there's one entry or one value per for all the rows available. In our case, we actually have multiple samples, each of only one feature, rather than multiple features for only one sample. So we want to reshape this. Now, this is a place where, again, we're going to run into an error that's going to confuse new people quite often. And the issue is that we're going to want to reshape this. Okay, so it tells us to reshape. Well, if you actually look at this carefully, you see the value it actually got is array, even though we have here is this pandas series object. Under the hood, pandas and most other things you're going to work on in Python are going to be using numpy to do their math. And so it actually is going to be using this .values under the hood that to do the passing around of information. So if you go ahead and run that, we see that xtrain.values is actually the array it was using. And so this is the thing we actually have to work on with the reshape. And as suggested, we can use .reshape -1, 1 in order to fix our problem. Now, the question might be okay, what did that do? Well, this turned it into a 2D array. When we're reshaping it, we're saying how many rows and how many columns, if you're doing a two-dimensional object, are we reshaping this into. 1 is pretty self-explanatory. There's 1 column. -1 here just means as many as makes sense. So you could have handed this 3 or 37. It doesn't really matter. If you know you have 1 column, it's something, comma 1. And -1 is sort of the wild card of whatever makes the math work out. So we could have manually put in 16 in this case, but we can just use -1 to make our lives a little simpler and make the code a little more generic. All right. So if we do this, we now have a two-dimensional object that it can be used for fitting. Now, it'd be very tempting. Take this. Okay, here's our fix. Dot values that reshape -1, 1. Let's just copy this and go back here and plug it in. All right. And when we do this, we actually create another error. In fact, we get almost exactly the same error. And now it says that ypred is giving an error. Oh, it's because we also have it down here. And actually, this is a good case to also be careful about typing. I actually have a typo here. This is supposed to be xtest. I want to make a prediction on the test set. But we're still going to have an error. And the error here is now a different array. I have 4 values is not working out because I need the same reshape. So rather than just plugging in our little fix right at the problem, we should think about where the problem itself actually came from. The problem here is that we're supposed to be working with 2-dimensional arrays, and we're working for 1-dimensional arrays. And we did that way back up here when we first read the data. So we shouldn't be applying our solution line by line every time we want to fix this little piece. We really want to put our solution right here when we first pull the data from the data frame to define our initial x. And in this way, we're going to fix it downstream for the xtrain, the xtest, and anything else we do hereafter. Now, once you go back and change something higher in a code, an easy way to just reset, make sure everything works well, is to kernel, reset, or restart, and run all. So we can go ahead and do that. And take a quick moment to redo the imports. And after it runs, we'll see that, we are in fact able to do this. Now, we had a little break here because our little debug we were working on is no longer valid code because some of the attribute types changed, or really the data type changed. But we do see that our piece of interest here, which is y_model equals model.predict ytest, runs as well as the fitting. Great. So now we have successfully fit a model and figured out how to debug the most common sort of group of errors people run into when they first start doing this. All right. The next step is to say that we have a model. Is it any good? Now, this gives us to our third and last thing we're going to import from Sklearn package today. And we're going to import something from the metrics. Now, there are a huge number of metrics available inside the Sklearn package for examining things. Today, we're going to just be using mean squared error, which is the most appropriate metric when you're dealing with a regression type problem. All right, so we can go ahead and import this as we have everything else. Come on down. And then we can use this mean squared error to examine the difference between the actual y-test value and our predicted value. Now, mean squared error itself is not the most human interpretable thing, so we're actually going to go ahead and take the square root of it to give us the root mean squared error instead. All right, and so we can see that on average, our predictions are off by a value of 43 sit-ups. So is that any good? Well, one thing we can do to kind of get some idea of that is to look at the original values of sit-ups. We see they range from about 60 to about 210. So we can say if being off by 45 is within that range, reasonably so, but it doesn't directly answer whether we have a good value or not. So we really want to have something to compare against. So one way we can do this is we can make ourselves a little bit dumber model to compare to. All right, so say simple pred is equal to ytrain.mean. Right? So what this is going to be doing is just taking the mean of all the ytrain values and saying that's our prediction, right? That's maybe the dumbest prediction you can make. It's just, that's about whatever the average is, all right? And if we do that, we can then try to do the same thing and do mean squared error y_test versus our simple prediction, all right? And this seems like this should approximately work. However, we're going to run into another error. And this error is a bit like the first one we ran into. The error we run into here is singleton array 140.9375 cannot be considered a valid collection. Okay, that's a much less helpful error message. And all we really know, if you look at the stack trace here, is it happened on the line where we tried to use mean squared error with y-simple-pred. Now, this error is actually part of the same family of errors as the one we saw before, where we are using the wrong shape of object to handle what we're doing. The y prediction we have up here is a list of 4 values, or array of 4 values, to what's happening at those points. This y-simple-pred is a single value, hence singleton in the error message. And since it's a singleton and not a collection, i.e. a list or array of 4 values, the mean squared error tool doesn't know how to use it. So we actually need to do a little bit of Python magic here to convert this, instead of being a single value, into a collection of values by putting it into a list. And in this case, we're multiplying by 4, so it has the right number of items. And we'll find out that this works. Now, this is in some ways not the most obvious solution to things, right? Unless you've played around with Python a little bit, you wouldn't necessarily know that this is the way, or a way, in order to turn a single value into a list of 4 items, right? And this is just some kind of little syntax things you're going to have to kind of pick up along the way. But the underlying error here that you should and want to learn from today is that all of the packages and tool items available inside sklearn are written on the assumption that you are passing around these n-dimensional arrays or array-like, list-like objects that have certain shapes, and that as long as you get the shapes right, everything else kind of works out. But you just have to be aware that, well, regression is looking for a 2-dimensional x. Y can be actually 1-dimensional or 2-dimensional. It can be a little complicated in that case, though details will vary a little bit. It always comes down to just sort of having an awareness of shapes. And this awareness of shapes is actually something that translates into work people do when they're working graduate work on their machine learning tools and their custom packages. Is just the debugging aspect is, how do I keep the shapes of these increasingly more complicated things correct? And so getting the habit of focusing on the shapes and just making sure they're correct will really be a key skill as you get into machine learning. So we can see that our RMSE for our simplistic model of a simple mean is 74.4. And that for our logistic regression, we get a RMSE of 43.2. So there is a marked improvement using this linear regression over a very simplistic model, so we can have some confidence that the model is able to say something useful about the problem. Now, it'd also be nice, often, to visualize what we've done. So what we have done here is actually demonstrate what we need to do in a technical sense, but it isn't the most digestible for the common audience. So what we want to do is make a little scatter plot just to show that, oh, this is what's going on. Right, so let's go back up and we'll do one more set of imports up here. We're going to import matplotlib.pyplot as plt, and we're going to import numpy as np. Now these are two very commonly used tools, and along with pandas, these 3 lines of import are almost universal in everything you're going to be doing when you first get started. Pandas is a way of handling data tables and doing some reading and writing. Matplotlib is a way of doing some visualization. There's some other tools like Seaborn and Bouquet out there that you may get into using more, but I recommend at least playing with Matplotlib to start off with. And then NumPy is the way you actually do the math. So in so much as things are already being handled for you by sklearn or whatever other tool in terms of wrapping and doing the math for you, sometimes you just need to reach in to grab some data and take the mean, take an exponential, something like that, and NumPy is the way you're going to do that. So these are pretty much universal tools. So universal, in fact, that you'll often look at things online and they'll use np dot something and not tell you what np is. And you just have to know that pd is pandas, plt is matplotlib .pyplot, and numpy is np. So now we have our tools, and let's make sure to run our cell. We can come on down and we can make a simple plot. So we're just going to do plt.scatter xtrain ytrain, and then plt.scatter xtest ytest. All right, and if we do that, we get a nice little plot here showing some values. But big caveat here is it's tempting to say, okay, I can interpret this plot and figure out what's going on here. And that's okay in the moment, but 3 months from now, if you come back and look at this, you're going to have no idea what these axes are without looking back and reading the code carefully. So do yourself a favor and put some basic labels on your plots so that when you come back and try to debug what you're doing or pull from it for an example for something you're doing in future, you know what's going on. And I can't tell you the number of times this has saved people time and energy just to take 10 seconds to put a little bit of a label on their plot so they know what's going on later on. All right, so then we have sit-ups versus chin-ups. The blue points here were the training set, the orange was the testing set, and we can see that, okay, there's some sort of linear looking pattern you can make out roughly. All right, so that's the data. Now where is our prediction? Well, to get our prediction, we're going to need to synthesize some values. To do that, we're going to take advantage of np.linspace. np.linspace is going to generate a set of numbers for us of over some range. In this case, we want to go take values that go from the minimum value in the X train, okay, so about 1, to the maximum value in the X train, okay, about 17. And we're going to want a few points along the way. Let's just say 100. Right? And so this just gives us that range of values to work with. And if you may remember earlier, we had issue of 2D versus 1D. So let's just take a moment now and do reshape -1, 1. All right. So just to wrap up here, .min, .max, .reshape are all methods available to NumPy objects that are just built in. And there's a couple of other ones as well you'll get into using. But these are just the standard ones you should be used to thinking about. Oh, I just need to perform transformation, min, max, or reshape, and the tool is available there. All right. So now we have some X values to look at. We need to know the corresponding Y values for them on the plot. So we can do that by using our model to make predictions on this range of different values. And then we can do plt.plot, because we want to make a line now instead of a scatter plot of points, and simply plot our X and Y values. Now, this way of writing it up here is a little more general. In the case of a linear fit, you can just define 2 points and draw a line between them. But if you have some more complicated model with some more complicated curve, you could fill in this by having 100 points and drawing little lines between all of them in this fashion. You get something that's a little more robust and can cover whatever's going on. In terms of the data itself, we can see that we are able to get a pretty reasonable looking fit. The blue curve or line came from the blue points, and we can see that the values of the orange points that we're predicting are well within line of that. We can also see that there is some just inescapable error. So if we look, for example, these 2 orange points that in our test set, they have the same value of X, but they have different values of Y, or chin-ups. So given that they have exactly the same inputs, there's no way the model can make different predictions. So the best we could ever hope for is that the model makes a prediction somewhere between those 2 points, and it does. So in that sense, we should feel pretty confident about, in terms of the inputs we're using, how good the model is doing with that RMSE, that you just can't do much better than that. So with that, we've constructed about the smallest possible example of using machine learning to fit data. However, your curiosity should be raising lots of interesting questions about this process in the back of your mind. So we saw, for example, that we could use the sit-ups to predict the number of chin-ups that people were able to perform. Well, what if we use a different column? You could go back, you could change the columns, you could try that out. And you could also ask questions about, well, okay, this model we got here for linear regression is as good as we could do with using this one input variable. What if you use multiple input variables? What if we change from using linear regression to some other model form? And these are all things that are relatively small edits in the actual code. It just means changing a few variables, changing what you import, and you can pretty much use the same approximate boilerplate for most sklearn things. Now, as you develop more complicated questions about, again, what if I include more variables? What if I want to, for example, have some more complicated treatment of the pre-processing of the data? Then things get interesting. And one important caveat I'll mention here is that you'll notice in our plot, as in the work before, there's no scaling or rescaling of the inputs. Our sit-ups go from 1 to 17. Our chin-ups go from about 50 to about 250. It's common to normalize data beforehand. I didn't want to include it here today because it's a little more interpretable, especially with the plot for people getting started, if we can leave off that normalization bit. But as you do get to other models, that is an important thing to consider. Thanks for watching, and a special thanks to those whose donations help fund and sustain creating content like this. As always, the code produced today is available on GitHub through a link in the description. Remember to like, subscribe, push all the buttons, click all the things, and I'll see you next time.